Kurt Gödel broke everything. Most famously, he broke mathematics with his incompleteness theorem, showing that all formal systems contain true statements that can't be proved within said system. In studying for his US naturalization interview, he claimed to have discovered a legal means by which the US Republic could be broken, could be transitioned into a fascist dictatorship. His good friend Albert Einstein, along with Oscar Morgenstern, insisted on accompanying to his interview in the hope of stopping him from blurting out his proof, which he very nearly did anyway. Oh, and speaking of Einstein, once, as a birthday present, Gödel gave Einstein a time machine universe, a solution to Einstein's equations that proved that even general relativity is broken. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Universe in a Black Hole t-shirt and hoodie. If you believe we're trapped inside a black hole, where space and time swapped roles and the Big Bang was just the other side of a collapse, then this is the shirt for you. We're also still offering up our Black Hole Light Curves desktop and gaming mat that shows the ways light is warped by the gravity of a black hole. Plus, our UV Glow Kerr rotating black hole designs and dark energy mugs are all still available. Links in the description. Now, onto the episode. It's not an exaggeration to say that Gödel and Einstein were best friends. The aging Einstein once said that the only reason he continued to show up at Princeton was for his walks with Gödel. And so, when the occasion of Einstein's 70th birthday approached, it's no surprise that Gödel enthusiastically agreed to contribute to a book of tributes to Einstein's work. At first, Gödel thought to write a reflection on the relationship between Einsteinian spacetime and the ideas of the philosopher Immanuel Kant. As was his wont, Gödel fell down a rabbit hole, and in the process of writing this one essay, he came to understand general relativity as well as anyone in the world. And then he stumbled on something deeply worrying, an inconsistency at the core of his best friend's theory. The rabbit hole deepened. The deadline for the essay came and went, but so important was Gödel's contribution that the book had to wait. When he was finally done, the reason for the obsession became clear. Gödel had found a solution to the Einstein equation, the core of general relativity, that proves that Einstein's theory by itself does not guarantee a clean chain of cause and effect like it was supposed to. He'd built a spacetime metric, a universe, where every point in space and time there exist return loops that can bring you back to the location before you left. Now, by the time of Gödel's discovery, we already knew of solutions to the Einstein equation that allow time travel, but all of them require something that can be argued is impossible: negative energy density. So just add a prohibition of this impossible stuff, and the broken solutions go away. This prohibition is called the weak energy condition. With the Einstein equation plus the weak energy condition, a deterministic universe with unambiguous causal ordering seemed guaranteed. That is, until Gödel. He found a new way to time travel and to break causal structure with no impossible ingredients required. And the result is the Gödel universe, where time travel isn't just possible, it's inevitable. So let's take a trip into the Gödel universe, first by time traveling back to Relativity 101. In relativity theory, space and time are not clearly separated. They're both part of a four-dimensional object called spacetime. Depending on motion and gravity, space and time become mixed, trading into each other. The classic way to depict this is with a space-time diagram, with just one dimension of space. Everything moves up through time, but if you're also moving through space, you move on a sloped line. Shallower is faster, and 45 degrees represents the speed of light. Because nothing can travel faster than light, you can only ever influence parts of the future in this cone, your future light cone. Meanwhile, your past light cone represents the parts of the past that could have had an influence on you. No possible signal could connect you to the regions that are outside these cones. So you can travel, or can have travelled, any path within these cones. We call these time-like paths because on these, your motion up through time is greater than your motion sideways through space. Paths into the forbidden zones are called space-like. More space than time is traversed in these, and that supposedly is impossible. But let's try anyway. Say we jump in our rocket ship and accelerate away from the Earth, quickly reaching a large fraction of light speed. Relativity tells us that my time axis shifts relative to the direction of axis back on Earth. From Earth's perspective, my time and space coordinates get mixed. My clock slows, my length contracts. If I actually reach the speed of light, my clock stops. And if I could go faster, well, from the perspective of at least some observers, my clock actually reverses and I appear to move backwards in time. This is equivalent to breaking free of your light cone. Once you can do that, the past is accessible to you. And a long time ago, we did some episodes that showed exactly how this works. The impossibility of superluminal motion is directly connected to the impossibility of time travel in special relativity. Both are baked in via the Lorentz transformation. This is absolute protection of the causal structure of spacetime in the absence of gravity. Gravity changes things because it bends the path of light, so it can tip our future light cone. For example, approaching the black hole, light paths are bent by the black hole's gravity, and so our light cone bends towards the event horizon, while our entire accessible future ends up lying inside the black hole. And below the event horizon, the light cone tips fully sideways, which means the down direction becomes our new time coordinate. Now, if you could turn around and keep your light cone aligned like this, you really could travel back in time. But in a black hole, you can't turn around, your future is only down. Well, let me actually revise that. In a rotating black hole, a Kerr black hole, there is a region deep within where angular motion becomes time-like. Space is spinning so quickly that a circular path gets you back to where you started at the same time that you left. We call this a closed time-like curve, a CTC. It's time-like in this case because you never violate relativity by leaving your forward light cone. These regions of the Kerr black hole may not even really exist, and in any case, it's a pretty useless sort of time travel because you're stuck behind the event horizon anyway. We can force closed time-like curves into the accessible parts of the universe by bending space-time in various exotic ways, wormholes, warp drives, etc. But in all cases, these require some sort of negative energy. But then came Gödel, of course. Even before Roy Kerr came up with the rotating black hole solution, Gödel realized that rotational motion was the key to time travel. The general effect he relies on is called frame dragging, the twisting of spacetime due to a rotating mass. And we've actually measured this. Gravity Probe B sent a gyroscope in orbit around the Earth. Now, a gyroscope is supposed to always point in the same direction. In fact, Gödel calls the device an inertial compass in his paper. But the gyroscope in Gravity Probe B slowly swiveled from its original pointing as it orbited due to both the gravitational curvature, but also due to the twisted spacetime, the frame dragging caused by Earth's rotation. This angular shift is also accompanied by a shift in time. But in the case of Earth's frame dragging, that is a far too weak an effect to be measured. But in principle, if you travel around the Earth the right way, your clock slows due to the angular motion. It's never enough to freeze time altogether though. Even around a rapidly rotating black hole, there are no closed time-like curves on the outside of the black hole, only deep within. But Gödel realized that this frame dragging effect could still break causality if it happens in a space-time where the effect can add up. Now, the key is to describe a space-time which has a fundamental twist to it everywhere. All points feel frame dragging, not just around single spinning objects. We say then that it has global vorticity. All spacetime points rotate relative to neighbours, not like every spot is spinning, but rather like there's a vortex of world lines in an infinite 4D spacetime that has no centre. There are other requirements. A negative curvature or hyperbolic geometry is needed to allow this centerless rotation, and a balance of smooth positive matter and negative dark energy are needed to keep this universe static in size. But tuned right, Gödel showed that such a universe can be full of closed time-like curves. Let's see what this looks like. This saddle shape is a representation of a two-dimensional hyperbolic space. We're reserving the z direction for time so that we can stack these planes to represent a 4D universe. Zooming in, it looks flat locally, but the negative curvature is still there. Now, you don't notice anything weird moving through this space, even though the underlying twist is there. You notice this when time moves forward and neighbouring particles start to follow twisted paths. From any point in this space, as you travel outwards, your light cone tilts relative to the reference frame of your starting point. And beyond a certain distance, the Gödel horizon, it has tilted far enough to allow travel back into the past. Or at least, to claw back some of the time you spent travelling. But with a carefully planned route, travelling in a loop, you can steer your future light cone to eventually contain your starting point. Another way to think about this is that by mixing time with the angular coordinate, your motion in a loop can take the place of your motion through time and can even reverse temporal motion. That's right, Gödel invented the time turner. Turn enough and you travel backwards in time. But with restrictions. You have to travel out beyond the Gödel horizon from your starting point, which means you can't just spin on the spot and move into the past. The time-travelling possibilities of the Gödel universe are fun, but they aren't the real point. The real point is that this solution to the Einstein equation is a counterexample to the idea that baseline general relativity, the Einstein equation plus the weak energy condition, are enough to ensure sensible universes. Before this, any valid GR spacetime could be sliced into layers of consecutive nows where the exact configuration of everything, the particles, the fields of each of those slices, can be used to generate the next slice. This perfect global determinism isn't true in Gödel's universe, and the past and future become tangled and not clearly definable. Gödel proved that general relativity doesn't guarantee spacetimes that have a rigid causal ordering, at least in some cases, like in Gödel's universe. We can't say whether A caused B or whether B caused A. And what Gödel really showed was that the prohibition against negative energy wasn't enough to ensure sensible universes. Others came along and proposed new conditions. Global hyperbolicity was proposed as an explicit requirement, which has nothing to do with the hyperbolic geometries. It basically just states that for any physically reasonable solution to general relativity, any constant time slice must fully determine the next constant time slice. And that has to be true however you do that time slicing. Then came Stephen Hawking's chronology protection conjecture, which argues that any spacetime that allows closed time-like curves is unstable. Feedback from time-traveling vacuum energy will cause the ultimate reverb and collapse the universe. So that's really what Gödel gave Einstein for his birthday, the impetus for future generations of physicists to keep working on Einstein's greatest theory. Gödel didn't really break GR, but he showed the rest of us where some of the few remaining cracks are, cracks which may, in time, lead new Einsteins and new Gödels to deeper theories. Really quite the birthday gift, Gödel's time-turning spacetime.